So now let's talk about finned surfaces. Remember, there's only two goals in heat transfer. Either get the heat transfer rate to go faster or slower, right? We're trying to get it to not happen at all, or we're trying to get it to go just as fast as it can within reason. So how can we enhance heat transfer? What could we do? Well, if we look at the convection equation, we notice that we've got basically three terms that determine the convective heat transfer rate. A lot of times the temperature difference we really can't do much about. That's usually the case. We've got a hot surface that needs to be cooled. That's why we're putting fins on it in the first place. And that surface is just going to be at whatever temperature that the process operates at. Maybe we could bring it down a little bit by enhanced heat transfer, but by and large that's the driving force for heat transfer, and it's the way it is. The convective heat transfer coefficient, H, also usually doesn't have a whole lot of variation. Now, one thing you can do is you can make the fluid that's convecting with the surface, you can push on it. In other words, you can make it convect. You can cause forced convection. I don't know how many of you work on computers or how long you've been working on them, but when I started working on computers, most heat sinks for processors did not have fans. They were just static finned surfaces, and only in the last, well, I guess 15 years or so, have processor fans become extremely common and on everything. You know, maybe even longer, maybe 20 years. I'm showing my age now. But the point is that eventually you get to a place where you need a higher heat transfer rate, and so the only way to do that is to add a fan and increase the convective heat transfer coefficient, H. But finned surfaces, the technique of finned surfaces is to increase the effective area available for heat transfer. So we kind of have to give something to get something more. So if you look at figure A, you'll see a surface that has no fin. The base area for the fin is already defined there, but there's no fin yet. And if we extrude a fin off of that area and create image B, well, now we've got a lot more area available for heat transfer. We've only got a base area of width times thickness of the fin, right? But with the fin extruded out a length L, now we've got that upper and lower surface, and the base area is just moved to the end of the fin. So we really didn't lose any area, we've just drastically increased the area available for heat transfer, and so the heat transfer rate should go up. Now the problem with this is that fins are not 100% efficient, and probably your intuition was kicking and screaming there for a minute saying, hey, wait a second, that won't work, there's something wrong there. Well, you're right. Let's talk about a fin. We've got to play with math just a little bit, and I'll kind of tell you where we're going. We're going to discover that actually the heat, because of heat transfer along the length of the fin is not so-called isothermal. It's not a perfect fin. As a matter of fact, the fin temperature dropping off to the end means that less and less heat is moving to the end, and therefore there's less and less temperature at the end, or a lower temperature. So ideally what we'd really like is for the fin to be the same temperature at the base as it is at the end. Well, then the heat transfer rate from that fin would be the maximum possible. And so you see we've got the convective heat transfer coefficient, the area of this fin, and then the driving force for heat transfer, which is simply the temperature of the fin, which would be TB since it would be isothermal, minus the temperature of whatever's convecting around the fin, whether it's a gas or a liquid or whatever it may be, usually air. Okay? And that would be the maximum heat transfer rate from this fin. But in reality, that's not the case. As a matter of fact, in reality, because of heat flow along the length of the fin, that cannot be the case. The temperature has to drop, because think about what happens. As thermal energy flows through this fin, some of it's going to flow out, right? Some of it's going to leave and go into the air. Well, that means that in the next bit of length, the temperature has to be lower. As a matter of fact, the temperature has to drop as you move out along the length of this fin for that reason. So fin efficiency is simply defined as the actual heat transfer rate divided by the maximum heat transfer rate, where the maximum heat transfer rate is the theoretical if the fin were isothermal. But since fins temperature vary along the length of the fin, they are not isothermal, and we need fin efficiency. So the way we'll usually use this is not to discover fin efficiency. That's already been measured for us for several geometries. Rather, we will use it to calculate the actual heat transfer rate based on the maximum heat transfer rate and the efficiency, which we'll find another way. So you can see this saves us the complication of dealing with a decreasing temperature along the length of the fin. We've got a couple of different charts in the book. You should find them, and you should certainly tab them. They are in Chapter 8, which is where we are. But we've got curves for 3 different types of fins on one graph. And the way you use this, it's a non-dimensional chart. You see the x-axis. I can never remember the name of that Greek character. I think it's xi or something like that. I call it the snake or the squiggle line, okay? Whatever you want to call it is okay. It is a dimensionless parameter, and it basically captures the relationship of the geometry of the fin, okay? So you see, for a pin fin like we were talking about, the equation for the x-axis parameter is L plus 1/4 d, quantity multiplied by the square root of 2h over k over d, where d is the diameter of the fin. And so that particular fin geometry follows the curve that is pointed to there. The simple rectangular fin, which is, it's a little confusing the way this is set up because the pin fin is sort of isometric, but the other two are cross sections. So imagine the other two, the triangular and rectangular fin, is simply being extruded out towards you. You can see the base material on the right and the fin on the left with geometry information about the thickness and the length of the fin. But anyway, you see the corresponding equations for those and which lines they belong to as well. But basically, once you calculate the x-axis parameter, you choose the appropriate curve, go up to it, and then go over to the left to read off on the y-axis the fin efficiency. Now, there are many different types of fins. You saw some. Here's some that are made by Train Corporation. They are a special type of fin that I believe they have a patent on. I ended up getting one of these. A buddy of mine knew I wanted to get a heat pump for my home, and he's a repairman, no, not a repairman, but he's a remodeler. And he said, hey, I've got this, I'm taking this out, they want a new system anyway, I don't know if it works or not, do you want to take it away? So I came and got it. It turned out it didn't work, so I recycled the thing. But it was the first time I ever saw this type of fin being used in a residential application. And it's a really interesting geometry. As a matter of fact, there's a video I'll have you watch about this type of fin. I'm not sure how much I like this fin. I'm used to the type that are just rectangular fins. They're just really thin strips of metal that go around the tubes, right? The tubes go through the metal. Because I can imagine, you know, when I'm cutting my grass, throwing grass against something like this on accident, it seems like it would get really stuck, but apparently they've done the research and said that this is superior and lasts longer and all that good stuff. Of course, I guess they're advertising for themselves too, but anyway, there's a video on this and I do want you to watch it. If you look at these with the older type of just straight fins, if they were pushed to the side, you could straighten them back out. I don't know how you would straighten these out. These are basically wrapped on a tube, and they're just pin fins sticking out radially in all directions. And once you smash them, they're pretty much done. This is a cross section of what one looks like. So you can see the flow area in the center, that darker gray area, and then all the fins sort of like a porcupine out around the tube. Now, that's not the only chart we have. It turns out there's another chart, and I'm getting ahead of myself. This is the usual type of heat exchanger that you see, where you've got pipes running through plates, and those plates can be modeled as rectangular fins, at least for our purposes. So there's another type of common fin that's more industrial in nature. I don't see these much in residential situations very often, but this is a fin where the pipe itself, instead of having pin fins coming off of it, it's got radial fins. And this is in the next page. If you found the first figure, this one is just turn the page once and you'll find it. Again, it's a dimensionless parameter on the x-axis, but this chart is only good for one geometry of fin. But the size of that ring, of each of those ring fins, I guess you could call them, or radial fins, the size of them determine which curve you're on, and you use it the same way. You calculate the geometry on the x-axis and then figure out which curve you're on, another equation, and then go up to that curve, read it off on the y-axis, and that gives you the fin efficiency. So again, don't think of fin efficiency as something where you'll have to compute it from first principles or something. You just go to a chart given the geometry of the fin and read it off. And understand, I'm not going to give you some curveball where I've given you a fin that's not in the book. I'm not going to do that. We'll only deal with the fins that are in the book. Now, fin efficiency and fin effectiveness are two different things. They're very different, and students often confuse the two. Fin effectiveness answers a different question. It basically says, is it useful? So I would suggest you find the fin effectiveness area of your text, and next to effectiveness write usefulness and put a question mark. Is it useful or is it not? And so if adding the fin increases the heat transfer rate, then it's useful. And we say that the fin effectiveness is greater than 1 because it actually enhances the heat transfer rate. If the fin serves as an insulator, if it actually resists heat transfer and does not do a good job of transferring heat, and so that the heat transfer rate would have been better with just the base area exposed, then our fin effectiveness is less than 1. If the fin doesn't affect it, then the fin effectiveness is equal to 1. So not all fins are effective. Remember I talked about processors a minute ago. Heat sinks on processors are typically made out of aluminum because aluminum has a high thermal conductivity. What if I thought I was going to grab some fiberglass insulation from my wall and use that as a heat sink on top of the processor? Well, that's not a very effective fin, right? That's a horrible idea. What if I just took a whole slab of aluminum and set it on top of the processor? Again, that's not very effective. Fin effectiveness is defined as the rate of heat transfer with the fin divided by the rate of heat transfer with no fin. Now remember, this is different than fin efficiency. Fin efficiency is talking about how fins are not ideal. They are not isothermal. Fin effectiveness is just whether the darn thing is useful in the first place. Okay, so it's the heat transfer rate with the fin divided by the heat transfer rate from that base area if the fins simply weren't there. Now, let's consider a long fin, because there's something instructional here we can learn from it. It turns out you can actually analyze heat transfer along the length of a fin, and if that fin is so-called long, what that really means is that the temperature at the end of the fin has gone all the way down to the temperature of the surrounding area. It doesn't mean it's actually infinite, but you can set up a differential equation accounting for the amount of heat that leaves along the sides and the amount of, I should say, thermal energy that is then transferred on and continues down the fin. So you can write a differential equation and solve it along the entire length of the fin. And if you do that, this is the equation you come up with. You have the temperature as a function of x position along the length of the fin minus the temperature of the bulk fluid, that's T infinity, divided by the base temperature. Now remember, that's back at the connection point for the fin to the base area, minus again the temperature of the fluid around the fin. Anyway, that's equal to e to a negative power, where x is the position again, and there's some other things in there, and we'll talk about those. So this is the solution to the differential equation. Really, the left-hand side is called the dimensionless temperature, but don't worry about that. We'll talk about that a little bit later. If you write the fin effectiveness with this in mind, you can actually come up with the heat transfer rate for the fin. So Q dot fin is something you can actually write down, and this is how it comes out. Now you'll notice that we can rearrange things a little bit, and the temperature differences drop out, and all we're left with is what's beneath the square root. Now remember, this is theoretical, but we can learn something important from it. The first thing we note is that we should use high K values for materials that are going to be fins. In other words, fins should be made of things that are very thermally conductive. Well, that makes sense from intuition, right? K should be as high as possible. Now, it's not practical to make fins like this out of diamond, right? At least not yet. We haven't figured out a good manufacturing process for that. But we need something reasonably high, right, in terms of its thermal conductivity. That's what fins should be made of. That's why immediately you knew when I suggested using fiberglass insulation as a heat sink, you knew that was a bad idea. It does not have a high thermal conductivity. Now, notice that P over AC, well, what is that? Well, first of all, P is the perimeter. So in the case of our pin fin, it's just a round thing, right? It's just the perimeter length. But then that's divided by the cross-sectional area of the fin. So imagine looking at the fin from the end on, and what you would see is just a circle, right? The perimeter would be the outside of that circle, and then A sub C would just be the area you see inside of that circle. And what this says is that the perimeter to cross-sectional area ratio should be as high as possible. Now, if you think about a pin fin, you may not know this about geometry, but a circle is actually the smallest perimeter that holds the maximum area. That's exactly opposite of what you want. That's why pin fins that are round are actually not used all that much. I mean, you can use them, but they're not the most effective, because what you really want to do is have a lot of perimeter area and very low cross-sectional area. So just a minute ago I showed you a picture of some fins that were just, they were straight slabs, essentially. They were rectangular fins. That's the reason rectangular fins are used, and that's the reason that they're usually so thin, because the amount of area, if you look at the end of that fin, is very small, but the perimeter is very large because of the length of the fins on either side. Now, I'm not talking about the extruded length, I'm talking about the side lengths of the fin. So this should be as high as possible. So we want slender pin fins, or thin plate fins are ideal. Finally, we want high convective resistance. Well, that's not really the case, right? We'd like low resistance everywhere. So what do we mean? Well, notice that H is in the denominator. That means that it should be small. What does that really mean? Do we really want H to be small? Not really. What it means is that this fin will be most useful and most effective when we're having trouble getting the convection to take place, right? If there's a lot of convective resistance, in other words, a low convective heat transfer coefficient, that's when fins are particularly useful. If you think about a radiator in your car, you've probably seen one before, whether it's for your air conditioner or for the engine. And the radiator is just a heat exchanger, and usually they're made with thin plates, and so there's essentially fins on the outside with the air. Have you ever wondered if the fluid inside of the pipes of the radiator also have fins? Because think about it. It's a fluid flowing across the fins on the outside of the radiator, right? It's air. And it's also a fluid, of course it's a liquid, right? Antifreeze, or water, whatever the case may be. Some coolant is flowing on the inside. Well, they do not in fact put fins on the insides to aid in convection from the inside of the tube to the coolant. And the reason they don't do that, they don't bother with it, is because it's not particularly effective. It turns out that since the fluid flowing in the middle of the pipes in the radiator, since it's a fluid, it's a liquid in particular, it already has relatively low convective resistance. So it's not particularly useful. But air, being a gas, has very high convective resistance by comparison, and so fins are most useful on the outside of the pipes that make up the radiator. Now we can also talk about something that's a little bit different. It's overall fin effectiveness. Notice we talked about fin effectiveness of the fin versus just the base area, but there's usually a lot of so-called unfinned area. In that case, the total heat transfer rate from the surface is the heat transfer rate from the unfinned area that's not covered by fins, plus the heat transfer rate from the fins themselves. Quite often, the heat transfer rate from the fins themselves is a lot more than the heat transfer rate from the unfinned area, but this is again something that we need to consider. So we've got this unfinned area, you can see it circled there, and if we were to expand this equation, we can write the heat transfer rate from just the unfinned area, that's the first term, and the heat transfer rate from the finned area. You notice we have fin efficiency here in this case. Okay, so then we can rearrange and simplify a little bit, and then we can write an overall, or define an overall fin effectiveness as the heat transfer rate with the fins, so the total heat transfer rate from the whole heat sink, not just the fins, but also the unfinned area, divided by the total heat transfer rate if the surface had absolutely no fins.